The RAG pipeline is returning the right records. The similarity scores are strong. The retrieved chunks contain exactly the information the query requires. The response is still wrong. Not factually wrong, structurally wrong. The model is paraphrasing forecast or shorthand in ways that change the meaning, is treating a tornado rating as damage estimate rather than a wind speed classification. It is producing responses that a NOAA Weather Service forecaster would read and immediately distrust. Not because the facts are incorrect, but because the domain register is off. The model knows what is in the documents. It does not yet speak the language of the domain. That is a fine-tuning problem. This is fine-tuning when RAG is not enough. Models Part 15. RAG gives the model access to your data. Fine-tuning gives the model fluency in your domain. Section 1. What fine-tuning actually changes. Part 7 established that fine-tuning is additional training that adjusts the model's weights toward a specific domain. Part 8 established that those adjustments run the same training loop as pre-training, forward pass, loss calculation, backpropagation, weight update on a smaller domain-specific dataset. What that means in practice for the NOAA pipeline is worth being precise about. Fine-tuning does not add new facts to the model's weights in a retrievable form. It adjusts the model's behavior patterns toward the domain. A model fine-tuned on NOAA storm event records and National Weather Service documentation learns the vocabulary, the structural conventions, and the reasoning patterns that domain uses. It learns that EF2 refers to a specific wind speed range on the enhanced Fujita scale, not a generic domain descriptor. It learns that a forecaster narrative structured as a domain survey follows conventions that differ from a public warning. It learns to produce responses that sound like they come from someone who works in that domain rather than someone who has read about it. These are behavioral adjustments, not knowledge injections. The distinction matters because it defines what fine-tuning can and cannot fix. Fine-tuning cannot make the model know about events that occurred after its training cutoff. RAG handles that. Fine-tuning can make the model reason more accurately and communicate more fluently in the domain it was adapted to. RAG cannot do that. Section 2, when fine-tuning is worth doing. 3 conditions indicate fine-tuning is the right first step after RAG is running. First, domain terminology is being mishandled despite correct retrieval. If the model consistently misinterprets specialized vocabulary, abbreviations, or classification systems that appear in the retrieved context, the weight needs adjustment towards the domain. Prompt engineering can compensate for some terminology gaps but cannot substitute for weight-level domain adaptation when the gap is systematic. Second, output structure is inconsistent despite explicit system prompt guidance. If the model produces responses that deviate from the specified format on a meaningful percentage of queries even with clear system prompt instructions and examples, fine-tuning on correctly structured domain examples recalibrates the weight level behavior that the system prompt is failing to override. Third, the model is hallucinating domain-specific details that do not appear in retrieved context. A model that invents plausible-sounding storm damage figures or fabricates event classifications that were not in the retrieved chunks is filling domain knowledge gaps from its training distribution. Fine-tuning on real domain examples raises the threshold at which the model defaults to fabrication rather than acknowledging uncertainty. If none of these 3 conditions are present after RAG is running in production, fine-tuning is not the next step. The return on fine-tuning investment is highest when the gap it closes is specific and diagnosable. Fine-tuning a model that is already performing well to make it perform slightly better is rarely worth the time and operational complexity. Section 3. Preparing the training dataset. Fine-tuning requires a dataset of input-output pairs that demonstrate the behavior you want the model to learn. For the NOAA pipeline, that means pairs of storm event queries and correctly structured responses grounded in NOAA records. The quality of the training dataset determines the quality of the fine-tuned model more directly than any other variable in the fine-tuning process. A small dataset of high-quality examples produces better results than a large dataset of mediocre ones. For domain adaptation of the type this ARC requires, 500 to 1,500 carefully constructed examples is the practical target range. Below 500, the model does not see enough variation to generate the domain patterns reliably. Above 1,500, the returns diminish rapidly for behavioral adaptation tasks, and the training time increases without proportionally quality improvement. Each training example needs 3 components. The system prompt establishes the context the model will operate in during fine-tuning, which should match the production system prompt from Part 11. The user quality is a representative question a real user of the NOAA pipeline would ask. The assistant response is a correctly structured domain-fluent answer that the fine-tuned model should learn to produce. At this point in the article, there's a Claude Code prompt that you can see in the Substack firsthand. What you are asking Claude Code to build is a training data set generator that produces balanced domain representative examples directly from the NOAA corpus. The 5-query type distribution ensures that the fine-tuned model learns to handle the full range of queries the production pipeline will receive, rather than overfitting into a narrow query pattern. The validation split is what tells you during training whether the model is generalizing or memorizing. What success looks like is 900 training examples and 100 validation examples in CHAD format JSON-L. The query type distribution log shows roughly equal representation among the 5 types. Opening 10 random examples and reading them confirms the responses are factually grounded in the sample event records and structurally consistent with the production system prompt requirements. Section 4. Running the fine-tune with QLoRa. Part 7 introduced QLoRa as the technique that makes fine-tuning practical on consumer hardware. Part 8 explains why the base weight stays intact while adapter weights encode the domain adjustments. This step runs the actual fine-tuning process rather than the training dataset prepared above. QLoRa requires 3 configuration decisions before training begins. The rank parameter controls the capacity of the adapter weights. A rank of 16 is the standard starting point for behavioral adaptation tasks. Higher ranks increase adapter capacity and training time. For domain terminology and output structure adaptation, rank 16 is sufficient. The alpha parameter controls the scaling of the adapter's contribution to the model's output. Setting alpha to twice the rank value, 32 for a rank 16, is a standard configuration that the research literature consistently supports. The target model's parameter specifies which layers of the model receiving weight adapter weights. The target model parameter specifies which layers of the model receive adapter weights. Targeting the attention layers produces the best results for the behavioral adaptation this arc requires. At this point in the Claude Code prompt, at this point in the article, there is a second Claude Code prompt that you can see in the Substack firsthand. What you're asking Claude Code to build is a complete QLoRa fine-tuning pipeline that trains adapter weights on the NOAA domain examples, monitors for overfitting through validation loss tracking, applies early stopping to prevent catastrophic forgetting, and saves the adapter weights separately from the base model. Saving adapters separately means the base model remains intact, and the adapter can be updated or replaced without touching the base weights. What success looks like is training loss decreases across epochs. Validation loss tracks training loss without diverging, which would indicate overfitting. Early stopping does not trigger on the first epoch, which would indicate the learning rate is too high. The adapter weights appear in the model's NOAA adapter. The training summary shows final losses in the range of 0.8 to 1.2 for a well-configured domain adaptation run. Section 5. Loading and testing the fine-tuned model. The adapter weight produced by fine-tuning needs to be loaded alongside the base model before the fine-tuned behavior is available for inference. The adapter does not replace the base model. It modifies the output by adding its learned adjustments to the base model's computations at the targeted layers. At this point in the article, there is a third Claude Code prompt that you can see in the Substack firsthand. What you're asking Claude Code to build is a direct comparison between base model and fine-tuned model behavior on the same queries, with a domain terminology audit that makes the fine-tuning improvement measurable rather than subjective. The side-by-side comparison is what you show a stakeholder who asks whether fine-tuning is worth doing. The terminology check is what tells you whether the behavioral adjustment targeted the right gap. What success looks like is the fine-tuned model uses domain terminology more consistently than the base model on the test queries. The terminology check shows the improvement on the meteorological terms that the training data emphasized. The responses are structurally consistent with the production system prompt format. The base model responses serve as the baseline that makes the fine-tuning improved visible. Section 6. Managing the fine-tuned model in production. A fine-tuned model introduces versioning complexity that the base model deployment does not carry. The base model weights are stable. The adapter weights change every time fine-tuning runs on new data. Managing that complexity before it becomes a production problem requires 2 operational practices. First, Treat adapter weights as versioned artifacts. Every fine-tuning run produces a new adapter version. Store adapter versions with the training dataset version, the base model version, and the validation metrics that confirm the adapter's quality. The model registry concept from the machine learning series applies directly here. An adapter deployed to production without a registry entry is an untracked change to a production system. Second, validate the fine-tuned model against the RAG pipeline before deploying the adapter to production. A fine-tuning run that improves domain terminology but degrades retrieval ground behavior is not an improvement. The comparison script above tests the adapter in the isolation. The full pipeline test in Part 16 tests its context. Section 7. What RAG and fine-tuning together produce. A pipeline running both RAG and domain-adapted fine-tuned model has two complementary capabilities. RAG produces current specific traceable information from the corpus. Fine-tuning provides the domain fluency to reason over that information accurately and communicate the results in the register the domain requires. Neither is complete without the other for production deployment in a specialized domain. RAG without fine-tuning produces responses that are informally correct but domain naive. Fine-tuning without RAG produces responses that are domain fluent but informally limited to training cutoff. Together they produce a pipeline that knows what is in your corpus and knows how to talk about it. Next, assembly. Every component built across this arc gets connected into a single running system with the opinionated choices at each layer, explicit reasoning for each decision, and the full NOAA pipeline running at the end.